I'd now like to introduce Tania Watson, Research Liaison at the Baking Industry Research Trust. Tania spent more than 35 years in the food industry, including production, quality management systems, product development and research. In her current role with the Baking Industry Research Trust, Tania partnered with the BPA to address two of the baking industry's biggest sustainability challenges: large volumes of returned bread and reliance on single-use plastic packaging. Here's Tania to tell you more.
Moving a few things, which will save me knocking them off the podium later. Okay. So our project is entitled Bread Bags from Bread Returns, which I have to say, if it wasn't for some innovative thinking at Plant and Food Research, the baking industry wouldn't have come up with this idea. The research organisation that we worked with on this project is now known as the Bioeconomy Science Institute, but more specifically, at the time that the work was done, it was a collaboration between two legacy groups, Plant and Food Research for stage one and scaling up, and then Scion led the final work on the thermoplastic starch and confirming that this would work. So I'd like to acknowledge the researchers who are named on the title slide, in particular Gert-Jan Mogra, who is the lead researcher, particularly in stage one. And in particular, I'd like to acknowledge that he actually wrote the majority of this presentation and very generously allowed me to take it and edit it. We'd also like to acknowledge Convex Packaging, who supplied some commercial samples and technical advice. So our project goal was aimed to address two major sustainability issues that face industrial bread manufacturers globally: returned bread and single-use plastic bags. In fact, in the year 2022, when we collected the information for this project, there were 220 million plus bread bags a year being used in New Zealand. They do feed into the soft plastics recycling scheme, but technically are just a single-use product. And there was 9,600 tonnes of bread returns collected that year, coming back mainly from the supermarkets. Because we've got a baked fresh every day bread market in New Zealand, the bread only actually sits on the shelf in the supermarket for a maximum of 3 days, because it's only got a total 5-day shelf life, so we can't have it sitting there for too long, but it definitely does create issues with large volume of bread returns. So the initial target was to develop thermoplastic starch processing suitable for use with bread waste, focusing on obtaining a standardised, consistent polymer product. So the first thing that I'll explain very sort of briefly how you make starch thermoplastic. Basically, you take your starch product, mix it with a plasticizer. In our case, we used glycerol, put it through a twin screw extrusion, and you end up with thermoplastic starch. The advantages of this is that it's compostable, it behaves like plastic, it's clear enough to see through. The disadvantage is that it's brittle and hygroscopic, so the solution then is to blend with other polymers to make it more flexible. And it's already used, thermoplastic starch is already used in a range of commercial applications, for example, coffee cups, disposable cutlery, straws, pens, bags, that type of thing. So with our project, we did an initial lab scale stage one. We reviewed the IP landscape to check that we could actually work in the space, characterised the composition and scale of the bread waste in New Zealand to make sure that it was a suitable feed into this system, and that there was sufficient of it, and then we needed proof of principle extraction and testing. Then at stage 2, which was the work done by Scion, it was scaled up, it was blended, we made the thermoplastic starch, it was blended with a copolymer, and then also we did some techno-economic modelling. Next steps I'll explain later. So bread waste scale and distribution in New Zealand, as I explained earlier, there's about 9,600 tonnes of bread returns each year in New Zealand, and it's basically split like the population. 74% of it comes from the North Island and about 26% from the South Island. At the moment, the majority of it goes directly into animal feed, usually pigs, and some of the mixed bread is actually dried into crumbs, which then goes into animal feed as well. So the first thing that we looked at was this being the royal we, obviously, the researchers were doing the work, was starch extraction. And we looked at the compositional analysis of the bread waste. Okay, so key things here is that there's a large variation in the returned bread. You'll see there that the starch composition was from 67 up to 81%, so it's good to know that there is a large amount of starch in the waste, as that was what we needed to make the thermoplastic starch. There is some protein, 14.7 to 20.3%. There's soluble dietary fibre. What could be an issue if you're trying to blow bread bags is the insoluble dietary fibre, which was up to 8.4%. So we had to work on a way to remove that. The main point is there's lots of starch, which is what we're after, but protein and fibre what we need to control. So just quickly, starch in bread and dried breadcrumbs undergoes retrogradation and recrystallisation upon storage, and obviously if you're wanting to make a thermoplastic type product, a key for us was to remove the crystalline structures. Then just quickly, the bread returns were examined under the microscope. In the centre picture, basically you've got the bread matrix with some starch visible, but you'll see in white there's sort of like a plate-like and then long strings of the fibre. Because they were quite a bit larger than the starch granules, effectively, after we'd done an enzyme digestion, they could just be filtered out. So, starch extraction, different methods were tested and developed to extract the starches, and then the preferred method was scaled. This was just initially in the lab. The graph on the right, on the bottom axis, is the particle size. So the dark, higher peak, that's the sort of scale of the original product, and then to the right just shows that the larger particles, that was mainly the fibre that was able to be sieved out. Then what is quite important here is if you look at the total recovery, when we had the mixed bread crumb as a base, there's a lot of larger particles in that, so we got 55% recovery, and with the white bread it was 80%, because that's obviously got a lot lower fibre content. And the supernatant, basically that's when they mix the starch with water, spun it in a centrifuge, and the liquid at the top, that's actually quite important as well. We found out down the track. We were originally just planning to use the starch in the thermoplastic starch, but the supernatant, when we added that together, that added to the total recovery and yield, and we used that down the track as well as. So, after we'd made, just in the lab, basically mixed our extracted starch with a glycerol plasticizer, we were able to form some just on the bench, and then it was tested for tensile strength and how far you could stretch it before it broke. The wheat starch numbers are that was a native commercially available starch. Then we tested against a commercial thermoplastic starch, and then also with the bread starch. Bread starch obviously had a lower tensile strength, and the elongation at break sort of was variable. But it looked like we might be able to make what we wanted to. So following on from that, we went to stage 2, which was basically scaling up so that we could get enough to hand over of the starch to hand over to Scion and see what they could do with it. This worked well with the scaling up, and we obtained good yields. Particularly, we're up to 82% with starch plus supernatant with the white bread and 74.3% with the mixed bread. So this was where Scion took over with making thermoplastic starch and copolymer blends. First up was because we didn't have a lot of our bread starch extract, they worked with a commercial native starch, added glycerol, put it through a twin screw extruder to work out what was the best process that might work with the bread starch. You can see at the top we've got the low temperature, it's not fully plasticised, and as the temperature went up we ended up with a translucent product with a median temperature. And then they proved that the temperature and screw speed did not impact starch crystallinity, which is good because we don't want crystals formed, and the higher screw speed was easier to process, so that gave us the conditions to test with the bread starch. Then to add sort of to the plasticity, they added a copolymer, which is, and I think this is why I didn't become a chemist because I can't do these words, but polybutylene adipate terephthalate, so I'm going to call it PBAT, much easier to say, okay, which is basically a fully biodegradable and very flexible polymer. So if you mix it in with your thermoplastic starch, it changes the, increases the tensile strength and the elongation numbers. So, and by doing this with the commercial thermoplastic starch, basically established the conditions for copolymer compounding to achieve the mechanical properties we required for a bagging application. So then came the fun bit, was the process was then applied to the bread thermoplastic starch. And like any good science project, it didn't immediately work, but with a bit of tweaking, so that's the extruded material, we actually ended up with nice little bread thermoplastic starch pellets. So that was a success. And then what we had to do was look at the technical performance to work out whether or not we could potentially turn this into bread bags. Okay, so the top numbers relate to the commercial reference product, which was supplied by Convex. We don't actually know what copolymers were put in that, or plasticizers, but it's commercially available, and so you've got tensile strength of about 11.7. This should be the modulus, the middle one, that measures the flexibility of 0.14, and the elongation at break is quite long. Then commercial thermoplastic starch made with the native wheat extract and PBAT, that came in with a lower tensile strength, elongation was still quite good. And the bread one looks sort of in the range, but a little bit lower. But then when you compare it with the low density polyethylene material that current bread bags are actually blown from today, you'll see that that the bread thermoplastic starch PBAT blend actually fitted within the range where you want a tensile strength of at least 10 megapascals and an elongation of no less than 200%. So in other words, in theory, we've got a material that bread bags can be made from. So from there, because down the track, obviously things need to financially make sense, as a techno-economic analysis was worked on, which detailed the analysis of the capital that would need to be spent, operating costs, input parameters, output. It's a really big job with lots of equations, yeah, very briefly, it was to work out the net present value and what the profit could be made out of this. So the next graph actually looks like a really good story, and in actual fact is. The left axis is the cost of the thermoplastic starch per kilogram. The bottom axis is a log scale, shows bread return usage in tonnes per year. And what you've got is this is the cost of commercial thermoplastic starch. These are all the different costs involved with the bread product as they stack up. And as you'll see that this is the feedstock, or the waste bread. As that goes, you use more of that, the price comes down, and in theory, it's when you look at the cost of the commercially available product now, it looks like really good value. In actual fact, it is. But this is the big but, is when you look at the cost of goods sold and the cost per plastic bag, we have one major hiccup here, and that's the cost of a low-density polyethylene plastic bag that's used at the moment. It's about 1.5 cents per bag, okay? And even like this is the commercially available products, and while the cost of our bread thermoplastic starch bags looks as good compared with these, there's no way it's going to match the low-density polyethylene bags. Okay, so if ever we were forced away from single-use bags, it's worth revisiting to go to the compostable option. But at the moment, for economic reasons and not wanting to boost up the cost of a loaf of bread, industry will be sticking with their low-density polyethylene and encouraging our consumers to put it into the soft plastics recycling collection. So, conclusions are that New Zealand produces enough returned bread per year to fully replace the 220 plus million bread bags used per year. The tested mechanical properties of bread thermoplastic starch were within the range of the two reference materials, but on price alone it is challenging to compete with the low-cost options of low-density polyethylene. And the techno-economic analysis for preparing the TPS from returned bread found a net positive return in comparison to using the commercial polymers available. So where we're going next with this is if this had turned out to be sort of cost-effective from a bread bag price, we would pilot scale the starch extraction, blow form some bags, put some bread into it, and test the functionalities that are key to the baking industry. But what we are looking to do at the moment with BSI is look at coming up with a simpler and cheaper process. So basically develop a scalable process to directly convert bread returns. So skip the starch extraction step. So this should reduce the cost. We may lose some functionality as a trade-off, but hopefully, while we might not end up with a product we're thinking at this stage that could be used for blowing bags, we could potentially, for example, injection mould bread trays, which we use a lot of as well. And then finally, before I go, I would like to just briefly cover off what I think is a major benefit of working alongside BPA versus other contestable funders. We're always after looking for ways to leverage our funding, but what we found with BPA was an obvious advantage was that the application for funding process was not blind. You just didn't sort of fill out your forms, throw them into a black box and cross your fingers, okay? When we first presented our project to BPA, they thought our focus should be on harvesting the protein content, so it took a bit of backwards and forwards for us to explain that, well, for us, while the protein, if we extracted it, might have higher value, we had two issues that we thought this project could knock off. So that was the single-use plastic bags and the waste material. So we funded some pre-work to get going, prove that as an industry we were serious with this, and we appreciated the opportunity to have a discussion with BPA rather than just getting a no because they thought that we were on the wrong track. The initial project proposal was a full 4 stages, but BPA, after discussion, they said, well, we'll co-fund 1 and 2, and if that works, then you can come back. So we did come back eventually, and they, with promising results, so that we got co-funding for stages 3 and 4. So we appreciated the opportunity to receive feedback from BPA's Science Leadership Group and being able to respond by modifying our application before Science Leadership Group gave a recommendation to the BPA board. So it was much better than just being turned down with no discussion and having learned nothing in the process. So we got to develop our idea. There were sort of iterations going backwards and forwards. But we really appreciated the Science Leadership Group's feedback, made us think a bit more about things, and we were able to modify things to get the outcome that we wanted. Thank you. Oh, and just finally, I do have proof that we did manage to make the stuff. This is the toast, the bread thermoplastic starch. Does smell and look a little bit toasty, which we don't think would be an issue, and I'll put it on the BSI table later so that you can have a look if you want to.
Yeah, thanks, Tania. Thanks so much, Tania. I think it's a classic scenario where everything makes sense, probably apart from the cost of virgin plastic. And I think lots of the projects that we see and support will have their time, it just might not be right now. And I think it's a really great, relevant story. And also appreciate your reflections on how the BPA process works, because I agree that it is a really powerful process, that two-way discussion, and does strengthen the projects in the end. So thank you very much, Tania.